Today I'll be talking about minimum word error rate training with language model fusion for end-to-end speech recognition, a paper from Microsoft. End-to-end ASR systems directly map a sequence of acoustic features to a sequence of grapheme. The output can be word labels or subword tokens. The systems are trained on multi-domain data and then often perform poorly on specific domains. To adapt the system to a specific domain, an external language model is commonly used. This approach is known as language model fusion. An effective fusion method is shallow fusion, where the fusion happens during inference. In traditional inference, end-to-end model predicts an n-best list of hypotheses Y from input speech X. Each hypothesis is given a score of posterior probability from an end-to-end system model. The best hypothesis is selected with highest score Y hat. In shallow fusion inference, the score of each hypothesis is interpolated from end-to-end system score and an external language model score. The lambda t is interpolation weight for the target domain external language model. Besides external language model, internal language model integration was proposed to improve recognition performance on top of the shallow fusion. The internal language model was implicitly learned by end-to-end model on source domain data. The idea of internal language model integrations is to subtract the score of the internal language model during inference. In other words, we further reduce the effect of source domain when adapting to target domain. In general, the internal language model probability is estimated using end-to-end models without their encoder. This is an example of internal language model estimation for RNNT. An RNNT has three components. A label encoder encodes grapheme labels. A audio encoder encodes audio features. Neural networks receive the label embeddings and audio embedding to predict the probability distribution of the next label. We estimate the probability of internal language model by ignoring the audio encoder and set the audio embedding to zeros. The equation 3 shows how to integrate internal language model to shallow fusion. In the upcoming slides, when talking about LLME or internal language model estimation fusion, we refer to the equation 3 with both shallow fusion and internal language model estimation. Lambda t denotes interpolation weight of external language model. Lambda s denotes interpolation weight of internal language model. But there's issue in the language model fusion methods. The optimal values of language model interpolation weights, lambda, vary over a wide range of different datasets. It requires extensive weight tuning on well-matched validation sets. One possible reason is that the language model fusions happen in inference. In other words, the end-to-end model training is not aware of the language model fusion's effect. In this section, we present how language model fusion is integrated into training of end-to-end models. First, we present minimum word error rate training for end-to-end models as a baseline without language model fusion. Second, we present how shallow fusion is introduced into the MWER training. And lastly, we present how ILM fusion is introduced to the MWER training. So basically, during minimum word error training, the language model fusion is performed to obtain n-best hypotheses and their scores. Note that interpolation weights lambdas are fixed and predefined during training. The question are, after this MWER training, does the LM fusion work well for multiple domains with the same language model weight and same interpolation language model weight? The second question is, does the language model fusion generalize well for out-domain datasets with the same language model weights? In recent years, minimum word rate loss functions is used effectively in training end-to-end models. In this work, MWER was used to train the end-to-end baseline. MWER loss is approximate as expected number of word errors over the top end hypothesis yn y1 to yn of input speech x. In the MWER loss equation, P bar is normalized posterior probability. Basically, it's the posteriors of the hypothesis yn normalized by the sum of the posterior probabilities of our own hypothesis. Our yn y asterisk is number of word errors in the hypothesis yn compared to reference y asterisk. How do we integrate the shallow fusion into the MWER training? Basically, shallow fusion is performed during MWER training to generate n-best hypothesis of x. The p-bar is in now renormalized shallow fusion probability. Looking at the equation 10 of p-bar, we can see both posterior of end-to-end model and probability of external language model. Lastly, how do we integrate the ILM fusion into MWER training? Basically, ILM fusion is performed to generate n-best hypothesis using source domain end-to-end model, internal language model, and external language model. P-bar is the renormalized probability of ILM fusion. The probability of ILM fusion is defined in equation 13. Basically, it is posterior probability of end-to-end model multiplied by the probability of external language model and divided by probability of internal language model. We can ignore GX for now. In this section, we present two sets of evaluation to determine the robustness of their methods on multi-domain dataset and out-domain datasets. In this experiment, a streaming transformer transducer, we know that TT, is trained to minimize either MWER or MWER SF or NWER-ILME loss. Language model interpolation weights are predefined during this training and kept constant. The authors evaluate their methods with multi-domain language model on multi-domain datasets. Moreover, the author evaluate the models with out-domain language model on out-domain datasets. In the first test of evaluation, the authors showed effectiveness of their methods on multi-domain datasets. Firstly, they show the performance of traditional language model fusion methods and its robustness on multi-domain dataset. Then they show improved performance of their methods on the same dataset. Recall that in traditional fusion methods, interpolation weight lambda is tuned on dataset and used on dataset. In this experiment, Oracle weight is tuned directly on datasets. The second column of the tables show weight error rates of the baseline without language model fusion on 6 domains called meeting, search, keyboard, email, and comment. On average, the end-to-end model has a weight error rate of 11.43. To perform language model fusion, in the first case, the interpolation weights are tuned on core subset. Then, the Oracle core weights are used on other domains. Look at the column, the third and fourth column. We can see that both language model fusions achieve weight error rate reduction on core and search from 8.37% to 7.33% absolute weight error rate for core. But performance degrades on meeting, keyboard, and comments. These results indicate optimal language model weights fluctuate dramatically on different datasets. The author also did a cheating evaluation. Specifically, they performed language model fusion on each dataset with optimal weights tuned on each set. The last two columns of the table show the best performance of the language model fusion. Both language model fusion result in consistent weight error rate reduction, with ILLME performing better. Now we look at how well their training methods can get. Firstly, we present the NWER-SF trained transformer transducer with lambda t of 0.25. The NWER-SF improves NWER training by 3.1% relative weight error rate reduction. In terms of average weight error rate, from 12% to 11.07% absolute. The NWER-SF degrades the weight error rate on meeting and keyboard subsets by 9.1% and 5.3% relatively, respectively, which is unfortunate. Lastly, we present the NWER-ILLME chain transformer transducer. The ILLME fusion consistently performs the best on all subsets with NWER-ILLME training. The ILLME fusion achieves robust and significant weight error rate across multi-domains using the same language model and the same interpolation weights from 12% to 10.43% absolute good error rate on average. MWER ILME outperforms Oracle ILME Fusion on average, which is very interesting. From 10.43% versus 10.69% in previous slides. In the second set of evaluation, the authors explore the generalizability of their methods by integrating out-domain language models. The author used Libre Speech as their out-domain datasets. Given that their end-to-end model is trained on their in-house datasets, the NWER's SF outperforms NWER by 20.42% relative on average. And the NWER ILME performs best, achieving 21.7% relative wear rate reduction on average. In conclusion, in this work, language model fusion is performed in NWER training of transformer chain-based model to eliminate the need for language model weight tuning. ILME-based fusion outperform MWER and NWER SF trained models on average 8.8% and 5.8% relatively, respectively. MWER ILME even outperforms ILME-based fusion with Oracle language model weight. Both MWER SF and MWER ILME generalize well on out-domain SF with out-domain language model, achieving 20% relative weight error rate reduction.